Good morning to all of you. So please go through for a few minutes whatever we did last class. Yeah. Okay. Okay, I'll talk. Yeah, that means the current and the previous search directions are orthogonal to each other with respect to, yeah. Uh, from the figure, maybe you can only slightly reorient the vector. That's what I can say. No, they are the current and the previous, they are orthogonal with respect to matrix A. So they won't be looking like perpendicular in the when you draw in the, let's say, level set space. What the diagram I was trying to draw. If you are just taking orthogonal to each other, then of course it has to be perpendicular to the previous search direction, and then it would be actually become steepest descent direction. Because perpendicular means because already you have gone up to tangent, and so then the next direction perpendicular means it is going to be steepest descent direction. So are there any other questions? So let and these two questions I'll address and then I'll continue further. So the first one was about the classification of mode shapes into symmetric and anti-symmetric mode shapes. So typically, if you look at the, although this may not always be the case, but many a times you can do that. So classification of mode shapes into symmetric and anti-symmetric modes. So this was one question. And actually there are more classification in case of cells as well. So see, first is when we talk of symmetric or anti-symmetric modes, so first we will have to look at the symmetry of the structure. So let me take as an example, let us say that we have a simply supported beam, and and we want to do its free vibration analysis, so it is simply supported here. And for of course linear free vibration doesn't matter whether the ends are movable or immovable, but this is a simply supported beam. And as far as the boundary conditions are concerned, because the axial displacement is not important, let me for the timing make it exactly symmetric. So why to put two different boundary condition at the two ends. So let us say we have this as the beam, and the beam is of let us say in this case a uniform cross section. The boundary condition at this end and the boundary condition at this end, they are identical. So about center line, this structure is symmetric. So first thing is that the structure must be symmetric for this classification to be valid. So we know that we have identical material distribution, the cross section, boundary condition, this side and this side. And then if you, so first is that a structure is symmetric, in this case about center line. Now if you look at the various mode shapes when you do the free vibration analysis, so you will have first frequency, corresponding mode shape, second frequency and corresponding mode shapes. So if you see the mode shapes, the first mode would actually be coming out something like this. So you will find that in that case, this mode will also be symmetric about the center line. That is, the mode distribution. If I look at the displacement at an equal distance this side, so at this location, if I look at the displacement and if I look at this side, the displacement is exactly same. This so we call this mode as a symmetric mode. So this is the first mode shape, first mode, and this is actually symmetric. And obviously see now if you look at the second mode, so the first mode meaning is that either the whole structure is when it is vibrating in first mode, so either whole thing is moving up or whole thing is moving down, and it is that displacement is symmetric about the central line, that is line of symmetry of the structure. So this is line of symmetry of the structure. Now if you look at the second mode for this structure, and I am not actually solving for these modes, I am just telling you that the first mode would be like this, and what is the meaning of symmetry. So this is a symmetric mode, and we can exploit sometimes this, so that also I'll explain you. The second mode, if you look at, so the second mode would be actually two half waves, sine waves. Maybe my freehand sketching is very poor, so you may not get that identical thing. So this is now the center line. Now in this case, what you see that if I from the center line, that is line of structural symmetry, if I move at some distance this side and look at this displacement, and if I move by the same distance this side and look at this displacement, so these two displacements are equal and opposite. So one side the displacement is positive, magnitude is same, another side displacement is negative, magnitude is same. So this is known as antisymmetric mode. So this is actually second mode, and this is antisymmetric. Why it is antisymmetric? Because the displacement from the line of structural symmetry, if we look at the displacement at an equal distance on either side, so the displacements are equal and opposite. So that is why antisymmetric. So this is symmetric, they are same, and here it is antisymmetric. So the magnitude is same, but the direction is the opposite. So you call it as antisymmetric mode. So like if you look at the third mode again would look like. So you will have three sine waves, like they would be identical. So actually, you can think of sine wave with the complete sine wave with three identical half waves. You can let me try to sketch it more accurately. So the third mode would be something like this, and again in this you will find that this is the line of structural symmetry, and from this line if we go at equal distance this side or this side, we have the same displacement, magnitude as well as the sign. Or if I go at some larger distance this side, so if I move at equal distance both left and right from the line of structural symmetry, we get the same displacement. So again this is third mode, and this is again symmetric. So like that, if you look at the fourth mode in this case would be actually antisymmetric. So for such cases, now what is the use? Use is, so there would be this is the mode shape, there would be corresponding natural frequency, let us say some omega n1 or omega 1, omega 2, whatever notation you want to use, omega n2 corresponding to this, the natural frequency, let us say omega n3. Now at the center, since the second mode is having this, now again we call the points of maximum displacements as actually anti-node point, and the point of zero displacement are referred to as node point. Node not in the finite element sense, but in the sense of mode shapes or modal analysis. So like here this is anti-node point, because that is the location where you have maximum displacement if the structure is vibrating in this first mode. Yeah, and of course here you have got the zero displacement. So these are the node points of the mode, which are now these 2 points are of course coming from the boundary condition. Now if you look at the second mode, so there are 2 now anti-node points, that is one here and another here, and then there are 3 node points where there are zero displacement. So that is this location, and this location. So now if suppose there is an external excitation, I have a dynamic force, let us say some force F, and let us say that it is something like cos of omega ft. So this is a dynamic force, harmonic force basically, and obviously this force is acting at the center, and if omega f is close to the first natural frequency, that is omega n1, then you will find if you conduct the experiment, you will find that predominantly the structure is going to vibrate in this particular mode. So it would be moving up and down simultaneously all the points at a given time instant. But now So of course this omega f, let us say that no, we have a provision that no, we can vary this omega f, so we can have a sine sweep. And now if this omega f, let us say we keep on increasing this omega f, and there would be a situation when omega f will approach omega n2. So that means the forcing frequency is equal to second mode resonance frequency. Now what would be the vibrations of the beam? What would happen? Natural frequencies, that is forcing frequency omega f is same as natural frequency. You know the resonance, isn't it? Whenever the first criteria of resonance is that the natural frequency or the forcing frequency should be close to the natural frequency, or vice versa, we can say. And if it is so, then the structure is expected to vibrate with maximum amplitude. So you call that as resonance. Now, but in this case, when this omega f is close to omega n1, it is going to resonate and it would be vibrating in this particular mode. But when you are going to the second mode, and that means if I choose this omega f which is close to omega n2, so then what you will find is that the structure, although the natural forcing frequency is same as second mode natural frequency, but the vibrations would be actually very little. I mean theoretically the vibrations would be 0, because now for the second mode the force is acting at the node point. So it is not going to pump any energy to the structure, and therefore even if the forcing frequency is close to the natural frequency, but it will not vibrate because the force is acting at the node point of the structure. And of course if it is slightly because of some asymmetry, this node point is not exactly at the center, that is point of application of the load, so we might get some small vibrations, but predominantly you will find that the amplitude of vibration is going to be 0. But the same force, if you shift somewhere this location or somewhere here, then you will find with the same forcing frequency it will start vibrating with maximum possible amplitude. So of course then if omega f is close to omega n3, then it will start vibrating in this particular mode shape. And now if you look at the fourth mode, actually the dynamic force at center will not again excite the antisymmetric modes, that is second mode, fourth mode, sixth mode, and so on. It will excite only these. Now when you do the analysis, although this is a simple problem, but sometimes we want to reduce the computational time. So rather than modeling the whole structure, you might want to model only one half of this structure. So then what you do is you exploit the symmetry or antisymmetry boundary condition. So if you want to get from the half model, that means you just want to create this half of this structure from here to here. You don't want to model the full, because you will have then additional degrees of freedom and more computational time. So then you only model this. Here you will give whatever boundary conditions are there. Here we will give symmetry boundary condition. Symmetry boundary condition means in this case actually the slope is 0. You will have only non-zero deflection. So if you give the model this and give the symmetry boundary condition here, you will be able to get this mode, that of course you will be only getting half of this, but the frequency will get this, but you will not get this, because now you have given a symmetry boundary condition, and for this that symmetry boundary condition is not correct. This is anti-symmetric boundary condition. So you will get this mode, you will get this mode, and then you will get the fifth mode, and so on. If you want to get say second, fourth, sixth, then you will have to apply the anti-symmetry boundary condition here. Anti-symmetry means then the deflection is 0, like what you see in this particular mode, but the rotation is non-zero. So you can exploit sometimes this. So even though you have two category of modes, symmetric and anti-symmetric, but they can be extracted from half model of the structure. And theoretically, if your interest is only say to get a particular mode, so sometimes we do that. So if I want to just get, let's say the third mode, I can in fact just model this part of the structure and give the symmetry boundary condition. I will get this frequency which is equal to omega n3 was just by modeling this. But of course you will miss many other modes. So if you model half and give a symmetry boundary condition, you can get one set of modes. If you model half and give anti-symmetric boundary condition here, that is deflection 0, slope is non-zero, then you will get another set of anti-symmetric mode frequencies and mode shapes. So this is what is about of course if I see the boundary condition in the same problem, if I say that one end is, let us say, fixed and another end is simply supported. So if I have, let us say, this boundary condition, and now I want to again look at the do the modal analysis. So in this case, because what you see, the structure itself is not having any kind of symmetry here. because if I take half of the length as a center, although the cross sectional details and the material properties are same both sides, but the boundary condition here and here it is different. So then the mode is neither going to be symmetric nor going, all the modes will be neither symmetric nor antisymmetric. So in this case you have to model the full structure and give these boundary condition and then do the model analysis. So in this you won't be able to classify the modes into symmetric and antisymmetric modes. So this is like same thing if you consider say a plate structure, so you have similar kind of modes. So that is depending on, of course, so let us say all the edges are simply supported, that is transverse displacement is 0 and rotations about tangent they are allowed. So that means it can rotate like this, it can rotate here, it can have a non-zero slope about these lines. So in this case again if you do the modal analysis, free vibration analysis, you will one thing is that you find that this whole structure, because the boundary conditions are symmetric and geometry is symmetric. So now in this case you have two lines of symmetry of the structure itself. So this is one line, that means this entire structure is symmetric about this line, it is also symmetric about this line. So when you do modal analysis again you will find that you will have modes which are either symmetric with respect to both the structural symmetry lines, or the modes would be antisymmetric about both the structural symmetry lines, or another set now symmetric about one but antisymmetric about the other. So now here the modes would be under three categories: symmetric about both the structural symmetry lines, or modes antisymmetric about both these lines. One example would be like a whole thing is when it is vibrating, so the whole thing is going up or going down. So that's kind of mode which is symmetric about both the lines. But you can have part of it is say in one direction it is. So one possibility what I was trying to, so if I look at in this case the first mode, actually you will have, and if I plot the displacement distribution let us say along this line, so the displacement distribution would be like this, and if I move along this line, so the displacement distribution would be something like this, like this, and in between accordingly. So you will find here that this variation along the x is symmetric and variation along y is also symmetric. If I look at this y line here, that means if I in this itself if I try to plot, so what I am saying is that the displacement variation mode say variation is like this and along like this. Of course at this point the displacements are going to be same, so it will be like this. So this is symmetric about both the structural symmetry lines. Now I can have another mode in which I have two waves along let us say y and only one half wave along x, that is in this particular direction. So then that mode is going to be symmetric about this line and antisymmetric about this line. I can have two half waves, two sine waves basically along x and y, horizontal and vertical direction, and then you will have a mode which is antisymmetric about both the lines. So this is the classification of modes for this kind of structure, but the boundary conditions must be identical on all the four edges. Now if I change one edge say clamp, let us say rather than simply support, here you are clamping it, so rotation and displacement both are constrained. So then now this is no longer a structural symmetry line, because the boundary condition this side and this side they are different, but still this side and this side the same boundary condition. So this is the line of structural symmetry. So whatever modes you will get, they would be either symmetric about this line or antisymmetric about this line. But of course about the other line they are neither symmetric nor antisymmetric because of the boundary condition. So similarly when you, so this is about 2D. Now when you talk of cells, say for example a cylindrical cell. So if you have a cylindrical cell like this, so in this you have again the variation of the displacement, modal displacements along length as well as along the circumferential directions. So one possibility of modes is the axisymmetric modes. Axisymmetric means the whole cross section at a given location is either contracting or the whole cross section is expanding. So that means you have a cell that is typically referred to as breathing vibrations. So if you have this as a cell structure, so along the whole circumference, the whole thing, of course the displacement can vary along length, but at a particular length location, along axial location, the whole cross section is either expanding or contracting. So this is known as axisymmetric mode of vibration, and again this mode can be depending on along the length direction, if the boundary condition along this edge and the boundary condition along this edge, they are identical. So their distribution along the longitudinal direction can be classified either as symmetric or antisymmetric. Now the other possibility of deformation in this case, so this is known as, when you look at one cross section, so either it is moving in or the whole cross section is moving out, known as axisymmetric mode of vibration. If I look at, there is another possibility that if I look at one particular cross section, so the modes can have shapes like this, something like this. So the previous, in this case, now you see the displacement distribution along circumference is changing. So here what we call it as axisymmetric modes, and again they can be symmetric or antisymmetric about the axial symmetry line, and these are known as asymmetric. And again these can actually be symmetric or antisymmetric with respect to axial symmetry line, that is center line, if the boundary conditions are identical on both sides. And even here, if it's you want to theoretically, if you want to solve the find out natural frequency corresponding to in this case what we call, if you look at, if I let's say start from here, so this is one full sine wave and this another full sine wave, this is the third full sine wave. So we typically, in case of cylindrical cells, I mean closed, circumferentially closed cells, the circumferential distribution is identified in terms of number of full waves. So like this we usually call n is equal to 3 in this case. These are 3 full waves along the circumferential direction, and of course along the longitudinal direction you still refer half waves. So either say along the distribution of the displacement in this direction is designated by a wave number m, where m can be 1 means 1 half wave or 2 half waves or 3 half waves, like I was talking about in case of beams. So at a given circumferential location the distribution can be 1 half sine or 2 half sines or 3 half sines. So these are known as asymmetric modes. And again, if you want to know, although if you model the full you can get all the modes, but if you want to optimize the computational time, you can actually just model if you want to get the frequencies corresponding to n equal to 3. So you just model this section of the cell from here to here. This location you give the symmetric boundary condition, here you give antisymmetric boundary condition. With that sector you will get the frequency corresponding to this n equal to 3. Of course are its multiples basically, so n equal to 6, 9, 12, you can get all of those frequencies. So this is about sometimes you can exploit the symmetry or antisymmetry boundary conditions to reduce the computational time when you are doing model analysis. Of course when you are doing a force response analysis, now depending on the force, because it can excite both symmetric as well as antisymmetric modes, depending on of course the excitation, you might have to do a full model, or if the force is also symmetric, you are sure that it is going to only excite symmetric modes, you can still do the half model like I was talking about for the beam. So this was one question, and about the classification of modes. Of course this is part of dynamics of vibration course you do. Therein you study more details about all these different kinds of modes you get in continuous structures. Then another question was about this conjugate gradient method. So I think so question was in terms of graphically when we look at, so what we had said that we start with of course the descent direction as the steepest descent direction. So let's say we have some function whose minimum is somewhere here, and we start from some point, and these are the contours of constant function values. So let us say we start somewhere here, and in this case first we find the steepest descent direction. So we go say somewhere there and hit a tangent to another basically contour of constant function value. So you go here like this, and you find that ultimately up to here, if you move in this direction starting from this point, this we had said as d naught, and then this is the new solution which is d1, and this distance from here to here was designated by alpha naught. So then what we said is, now if I use the steepest descent direction for the subsequent iteration, then actually I will be moving in this direction here like this, which is normal to this particular surface. So this initial direction is becoming tangent here. It was normal at a starting point, but tangent at the end point, because beyond that if you go, again the function value is going to increase. So if I use just go normal to this, then it is going to be essentially a steepest descent direction again. But what we do when we had said that the new search direction R, let's say we had said that as R1. So R1 is orthogonal to initial search direction here. Let us say this we said as R0 with respect to matrix A. Then only we are getting a new search direction, which is say something like this, not this, but it is actually this. So we said that the R1 transpose into A into R0, this must be equal to 0. So this was the orthogonality condition. If you simply say R1 transpose into R0 equal to 0, then you are going to get to the basically steepest descent direction. So it would then become the steepest descent method, not the conjugate gradient method. So that is why we are introducing in between this matrix A, the coefficient matrix which was coming in the simultaneous equations we were solving. So this was another question. Is there any other question? So okay, then let me continue. So the last class we started with eigenvalue problems, and I had discussed about so this is actually a brief introduction, although most of the methods which you encounter or use some are the other variant of these. So one we said was the determinant method, determinant based method. So this we already discussed. The second was transformation based, and one example we took was Jacobi iteration method for a general case. So what here you are doing, again I think I will repeat this. So maybe I think I am taking a little more time. So Jacobi method. So in this what you are doing is essentially idea is finally to transform both stiffness and mass matrices into diagonal matrices by using a set of transformations. So that is what essentially we are doing. So what I was saying that we have this eigenvalue problem that omega n square m into dn is equal to k into dn. So this is our general eigenvalue problem, and in general you are having no off diagonal elements in k and m, both non-zero. Of course, if m is used as a lumped matrix, then lumped mass matrix, then it would have non-zero, all the off diagonal terms would be 0. Otherwise, in general, they are having non-zero off diagonal elements. So then, what we are doing is we have using series of transformations. You are transforming them to finally diagonal matrices. So that is what exactly we are doing. But then, how do we decide those transformations? So we said that if I look at the K matrix itself, similarly for M. So K matrix is like has a number of rows and columns. So K12, K13, and so on. K12 and K22, K23, and like that. So you have these rows and columns. So what we can sequentially do is first we construct a transformation matrix to make this K12, and similarly in the mass matrix M1 to 0. And for that we said that what should be the form of the transformation matrix and how to find out that parameter. So I had said that if you want to make K1 to 0, so that is the first transformation matrix we are writing. So this T1 we choose it such a way that now one is 1, another is 2. So it's involving first row, second column, or second row, first column. So and rest of the actually if you take this transformation matrix to be identity matrix, then if you multiply T1 transpose K into T1, you are going to get the same K matrix. There is no effect of that transformation as far as the K is concerned. So then starting point of course is the diagonal matrix, but then since we want to make this 0, so in the transformation matrix appropriately we introduce off diagonal elements. So this is 1, and since we want to make 1 to 0, so we introduce one parameter here, and this because this is also the second row and first column, so we introduce a parameter beta here. This is 1. Rest of the things are 0. So it's like otherwise identity matrix. So here you have 0 0 1 0 0 0 0 0 1 and so on. So now what you do, this is your transformation matrix. Then what you will do is you will write a say a transform matrix at first label, let us say call it as K1. So K1 you will be writing as say T1 transpose into K into T1. After this multiplication you are going to get a transformed K matrix, and in that what you would be doing is you would be saying that K12 should be 0, K21 should be equal to 0. Of course they would be identical because the matrix is symmetric. So finally you will find that you want to make this even though T1 is not symmetric, but when you do T1 transpose K into T1, the transformed matrix elements, that is K1 is going to be symmetric. So one condition then you are going to say that in the transformed stiffness matrix K12 equal to 0, that is one condition to find out this alpha and beta, and then similarly you will find the transformed mass matrix say M1. So that is also same way T1 transpose into M into T1. You do this, after the multiplication you will get the transformed M matrix. In that you say M12 equal to 0 in the case of transformed matrices. So from those two conditions you find out this alpha and beta, and then once you have alpha beta, then finally you have your T1, and then finally these transformed matrices. So this you do once, then now K12 and M12 have become 0. Then you similarly now take another transformation matrix and make K13 0. In the now you will not be working with the original K or M matrices, but subsequently you will be working with new K1 and M1 matrices. So now we will construct say another transformation matrix T2, and wherein you want to make 1 3 0, so you will have entry here alpha for first row third column, and similarly say beta in first column third row, and rest of the things are basically unity along the main diagonal. And then you repeat throughout, try to make all the of diagonal elements 0, but in the process you will find that the first stage we would have made K12 0, but when we make K13 0, K12 would become non-zero, M12 would become non-zero. But we continue that, we go till last location, that is finally we will be somewhere here wherein we will have Kn minus 1 comma n. So we will make starting with first K12, K13 up to K1n, then K23, K24 and so on. We will make try to make all of them 0 up to here, and then we will repeat this process all of again. So we will come back to the whatever finally transformed matrices we have got, final one, and then again in that we will try to make K12 0, K13 0. So they will repeat this. So one cycle means all the off diagonal elements once we try to make them 0. That's one cycle. Then we start the second cycle, and so if you do this number of times, you will finally find that all the off diagonal elements would be nearly 0. So this is what is known as this Jacobi method. That is what I had discussed. So obviously you can solve a simple problem like if you have a matrices of size 2 by 2, so that one transformation will obviously make the matrices diagonal. So that one step, but suppose if you have make it 3 by 3 matrices, you take a simple example, just know wherein you have 3 by 3 matrices, you will find that you have to do the number of iterations, because then K12, K1 through K23, and when you finally would have made K230, you will find that 1, 2, 1, 3 are non-zero, so then again repeat over there. So you might do 3, 4 cycles, and finally you will find that the matrices K and M are diagonal matrices. So that was the Jacobi iteration method I had said, and of course one can effectively do actually by writing a computer program for this, then you can actually study. Of course a simple problem like 2 by 2 matrix can be done, which is just one calculation in fact. So then the third category of methods are based on the vector iteration method. So the third one, vector iteration method, and in this also we have a number of them. So one is known as inverse vector iteration, forward vector iteration, simultaneous vector iteration, subspace iteration, Langstroth iteration. So there are a number of methods, but the basic idea is basically same. So as the name suggests, vector iteration. So I am going to just give actually one example. So as it says vector iteration, so vector means it's a modal vector of course, and you are trying to start with an initial guess, and through the iterations you are trying to make that vector same as one of the modal vector of the problem. So that is what is this vector iteration method. So here basic idea is that you start with the initial guess. So here no, you will start with an initial guess. Let me call no, so we are solving a problem, let us say again the same problem, that is omega n square into m into say dn is equal to k into dn. This is the generalized eigenvalue problem as we said. So here the starting point is an initial guess. So let us say that no, we start with an initial guess x1. This x1 is the guess for one of the mode shapes. And x1 is an initial guess. I am using a different notation. It is essentially guess of this one of the dn's. So d1 or d2 or d3, that is what we are saying. But in this what we do, so you start with an initial guess, and then you have to now do iterations, so that because your initial guess can be any arbitrary vector, and finally you will have to through the transform, basically iterations, you will have to make it same as one of these modes, either d1 or d2 or d3. So that's the basic idea here. Now to apply this, what we do, first we transform this, usually of course it's not necessary, to an standard eigenvalue problem. So when you do the standard eigenvalue problem, there are two ways of transformations. So one is that you can multiply k inverse to both sides, and then this problem can actually be written as, if you look at, so if I know the same problem, I can do it in two ways to convert into any standard form. So if I look at it, one way is that omega n of course is a scalar, and then I can say that k inverse into m into dn. The other side would be k inverse into k would be identity, so it would be only simply dn. And usually you solve eigenvalue problems as ax is equal to lambda x. So if you want to put in that format, so what I can do, because this side I have this matrix, so an omega n square I can take to the other side. So let me say that this is simply a matrix, that is k inverse into m is a, and into this dn is equal to, other side I will have 1 by omega n square again into dn, and now this you can call, let's say, lambda. So this is lambda into dn. So one way of writing this, where a is k inverse into m into dn is equal to lambda. So this form of the eigenvalue problem is referred to as standard eigenvalue problem, and this form is referred to as generalized eigenvalue problem, wherein both sides you have matrices here like m and k are there, and if you have matrix only on one side, then it is referred to as standard eigenvalue problem. So this is one way. For this, lambda is 1 by omega n square. So for if you get lambda, then you have to take inverse of that and square root to get finally omega n. The other way is, now I multiply m inverse on both sides. So what I can do is, if I multiply m inverse on both sides, and let me write the left right hand side first. So I can write the same thing as m inverse into k into dn is equal to, this side you will get omega n square, m inverse into m would be identity matrix, so you will simply get this is equal to dn. And this you can I am just using as a notation, this a here and a here, they are different, but I just want to or no, you want to say some other notation, you say a bar, okay, a bar into dn is equal to, this is lambda, which is now omega n square into dn. So this is another form of eigenvalue problem. Here see lambda is omega n square, here lambda is 1 by omega n square. So in the vector iteration, if we start try to solve this problem, we basically use this information, then it is known as inverse iteration method. Inverse means it is giving us finally 1 by omega n square. Now if you are solving this eigenvalue problem here, where a is k inverse into m. If we solve this problem through vector iteration approach, where a here is m inverse into k, and then lambda is equal to omega n square, this is known as forward iteration method. So there are two vector iteration method, either the inverse iteration method. So if you are solving this is known as hello. हेलो सॉरी हेलो हाँ जी हाँ मैं हाँ जी वो एल एच नहीं मैं लगभग आप यहीं ना LH316 में है. हाँ LH316 में हूँ बेटा मैं, यहीं पर उनका सर्टिफिकेट है. हाँ 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 ओके बाय. किसी का सर्टिफिकेट है उसको. सॉरी एक्चुअली someone's certificate is with me and he has to urgently take it for some interview. So that is why sorry for this disturbance. So what I was saying that when we convert this generalized eigenvalue problem in this form and then try to solve the problem, this is known as inverse iteration method. And if we use the same vector iteration approach and solve this problem, that is we take A as M inverse K, then this is known as, because here this word inverse is coming because here the eigenvalue is 1 by omega n square, inverse of the square of natural frequency, and that is why this terminology here. And here we are getting eigenvalue which is directly omega n square. So this is known as forward iteration method. Now how do we do this? So essentially, as I said, so either you can use inverse iteration method or you can use forward iteration method. You start with an initial guess, and then what you do, if you multiply this initial guess by pre-multiply by A n number of times. So when you do that sufficiently large number of times, you will find that if I am doing this is always going to converge to that mode shape would transform to a mode shape corresponding to largest value of lambda. So that means I start with an initial guess, and then I take another vector x2 which is A into x1, and then take the third vector x3 which is A into x2 and so on. So if I do that n number of times, I will find that finally whatever resulting vector is coming out, that vector would be corresponding to a mode shape corresponding to largest value of lambda. And since in this case largest lambda means will be corresponding to smallest omega n. So if you want to get the smallest value of omega n, you actually use inverse iteration method. If you want to use the largest value of omega n, which is not important in case of structural dynamics, but it might be important, say for example, to decide delta t in case of explicit integration techniques. So then you might use this forward iteration method, and finally when you start with any arbitrary initial guess, maybe all the elements of this x are unity, you start with that and keep on multiplying first a into x1, then x2 a into x2, then you get x3, and then a into x3, a into x4 and so on. When you do that sufficiently large number of times, you will find that whatever vector finally you get, that vector would be corresponding to a largest value of lambda. And in this case, in case of forward iteration, if my a bar here is m inverse into k, then that would be largest value of omega n. So this is known as forward iteration method. And since here you are of course working with only one vector, so finally you are going to get to only one particular mode, either the largest value of lambda, in this case finally corresponding to smallest value of omega n, that is fundamental mode, and here it will be largest value of omega n itself. So this is a basic idea in case of vector iteration method. So then what you do, let me first give you a proof that how it works. So now proof of that it works. So what you do, let's say initial guess. Now I am taking an initial guess, and which is arbitrary. So if it is arbitrary, I can always express this initial guess as a linear combination of all the modes of the structure. So the linear combination of modes of the structure meaning is, say some constant C1 into first modal vector plus another constant C2 into second modal vector plus third constant C3 into third modal vector, and plus finally Cn into Dn. So what, although we are not going to work out when we use the method, we are not going to this. We are going to straight away assume this. Maybe as I said, all the elements are unity. 1 1 1 1 1. Whole vector is 1 1 1 is taken. But what I am saying that whatever we are assuming, this can be expressed as a linear combination of first mode, second mode, third mode, all the modes of the discretization, nth mode. And now let us see what would happen if I multiply this whole thing by A, whether it is inverse iteration or forward iteration. No, I am just saying that matrix as A. So if I do A pre-multiply by A, so I will have A here into x1. So this is I am multiplying left side, same thing I will do on the right hand side. So the right hand side what I will get is, see you are going to get right side C1 and A, I will write few terms here into D1 and plus no so on, no the other terms. So you can say finally you will have Cn into matrix A into Dn. So this I am just pre-multiplying both sides by A, that is what I am doing. Now as per the eigenvalue problem, what is this A into D1? Lambda times D1, isn't it? Because of the the eigenvalue problem, A lambda A Dn is equal to lambda Dn, and n can be 1, 2, 3. So this is simply you see that it is going to be C1 lambda into D1 and so on. The last term would be Cn into lambda n. This would be lambda n into Dn, because here we are considering the nth mode, whatever is the highest degrees of freedom in the system. So this is what you get. Now like this if I do, so this is the first time. Now if I call this as, let us say x2, let us call this vector as x2, the resulting vector. Now if I again do A into x2, what do I get? If I do now this, so x2 is already this, right? So now if I multiply again this with A, I will have A into D1, which is lambda times D1. So you will get actually lambda 1 square, so you will get C1 and lambda 1 square into D1 and plus Cn lambda n square into Dn, right, like that. So first one I just said x1, so if I do like this, say m number of times, so finally I will get, now this is my x3, so let me call this as x3, which is A into x2, and this is x3, so you will find that when this is x3, this is 2 here. So if I finally write say xm, that is after multiplying, let us say I put here 2, so 1 is higher, m plus 1. So xm plus 1, if you look at it, would be of the form C1 lambda 1 to the power m into D1 and plus say C2 lambda 2 to the power m into D2 and plus Cn, of course, lambda n to the power m into Dn. So this is what it is. Okay. I thought that someone was to come, so I was just. So this is what you get, that if you keep on multiplying by vector A, you get this finally, let us say we do this multiplication m times, so finally this is what we are going to get, vector x m plus 1 like this. And now in this, let us say that the eigenvalues are arranged here, let us say we are doing inverse iteration, so I mean any one of these. So let us say the eigenvalues are such that lambda 1 is the largest and lambda n is the smallest. Let us say these are arranged in that fashion. So let omega 1 would be the largest value, less than lambda 2, then lambda 2 is less than lambda 3 and so on. Finally you have lambda 1 n as the smallest value. Then what is going to happen? Then you will find that this term is going to be dominating, and these terms would become much smaller compared to this term. So what I can also do is that in this particular equation, then I can take lambda 1 to the power m as a common factor. So what I will have is lambda 1 to the power m, then here I will have C1 into D1 and plus C2 into lambda 2 by lambda 1 whole to the power m into D2, and the last one Cn lambda n by lambda 1 whole to the power m into Dn. So this is what I will have, right? Now since I said that if the eigenvalues are arranged in this manner, so compared to this term here, lambda 2 by lambda 1, when you raise to a higher power, it is going to approach to 0. So all these terms would approach to 0. So finally you can say that this would be approximately lambda 1 to the power m into C1 into D1. This is anyway a scalar multiplier. this is also some scalar constant C1. So finally you would see this x m plus 1 is actually proportional to the mode shape corresponding to highest eigenvector of this standard eigenvalue problem, a lambda equal to ax equal to lambda x. So that means what? This is just a proof showing that if we do this multiplication, pre-multiply the initial starting vector m number of times with a, then finally whatever resulting vector we will get would be corresponding to the mode shape corresponding to highest eigenvalue of the problem. So this is the basic idea. So when you use the method, you start with, let's say, I take an example. Let us say that I want to solve an eigenvalue problem where I have say maybe the matrix is, I am just taking arbitrary, say we have just 2 by 2 matrices K12, K22, and into we have the here. So let us say that we have just this u1 and u2 are the elements of the eigenvector, and this is equal to, say you have omega n square into mass matrix. Let us say that is m11, and let us say that it's a lumped mass matrix. We have m11, m22, and into u1 and u2. Let us say that we have this form of the problem. So how we'll go about doing this? First is, if your interest is to find out the smallest omega n, then you use the inverse approach. That means both sides multiply by k inverse and then convert this into basically ax is equal to lambda x, where lambda is 1 by omega n square. So you will get the smallest value of omega n, and if you want the largest value, the second, obviously in this case there are only 2 eigenvalues. If you want the largest one, then you pre-multiply both sides by m inverse and then again convert ax is equal to lambda x form. So your starting guess here, see your starting x1 would be like you can take any one, say 1 1 or maybe 1 0, and then you repeat that process. You will have to then multiply your A matrix. If you are doing inverse approach, then your A is simply going to be k inverse into m. So this will be your A, and you do sufficiently a number of times. So finally you will have to see that that vector converges into a particular vector. So there some convergence check has to be done, and you keep on multiplying. You construct x2, x3, x4, and at the end you get a vector which is corresponding to, if your A is k inverse into m, then whatever vector you get would be corresponding to smallest value of omega n. So then you get x, say m plus 1, which is as I already said, you would have multiplied this, pre-multiplied by a m times. So then you will get x m plus 1. And then how do we calculate that eigenvalue lambda here? So to calculate the lambda, then what you do is, because our eigenvalue problem is A into here I said dn, right? So this dn. So we have A into dn is equal to lambda into dn. So we have got this. So what we can do is, now this dn we are approximating by basically x m plus 1. So what you can do, dn you are replacing it by x m plus 1. So you will be writing this as A into x m plus 1 is equal to lambda x m plus 1. Then it is going to give you the corresponding eigenvector. But then with this we cannot get as it is lambda value. So also pre-multiply by x m plus 1 transpose. So if you do that, then you can write the same thing as x m plus 1 transpose into A into x m plus 1 is equal to, right hand side you will have simply lambda times x m plus 1 transpose into x m plus 1. This is what you will get. Now you will see that this whole thing is scalar, because this might be some capital N by capital N matrix, and this is n by 1 and this is 1 by n after transpose. So finally it's a scalar number, and similarly this is x m plus 1 transpose is 1 by n, this is n by 1, multiplication is again a scalar number. So then from this you can directly get your lambda. So you can say that finally lambda will be this in the numerator divided by this in the denominator. So this will be x m plus 1 transpose into A into x m plus 1 divided by x m plus 1 transpose into xm plus 1. So this will give you lambda, which is actually 1 by omega n square, and this is largest value of 1 by omega n square, therefore smallest value of omega n. And so this is how you will actually apply this method, and you can, as I said, essentially you can either use the forward iteration or you can use inverse. If you use forward, you get largest omega n. If you use inverse, you will get the smallest omega n using this. Now if the problem is if we want more than one eigenvalue to extract, then what do we do with this method? Of course, there are other methods where you, rather than choosing initially starting with a single vector, you take a set of vectors, maybe 3, 4, 10, 20 vectors, and then you use the similar kind of iteration. So that's under the category of subspace iteration and basically Lang-Sauce, even the simultaneous iteration. But within this, if you want to do, let's say first I have got the lowest frequency. Yeah, okay, so I'm just going to conclude. So suppose I have got the lowest natural frequency, he has another class actually. So somehow I'm going slow, so I always think that let me take a little more so that I can cover whatever I wanted to do. So see what we can do if we want to, let us say first we got the, using the inverse iteration approach, we have got the smallest natural frequency, and now then we want to get the second lowest. Then what do we do? Yeah, so yeah, that's something similar one can actually do. So suppose now I have got the, using inverse iteration approach, I got the first frequency omega n and the corresponding omega 1, let me say, because n I am using as a subscript. So omega 1 and the corresponding mode shape d1. These I have got. And now using same inverse iteration, now I want to get omega 2 and the corresponding mode shape d2. Your starting guess is going to be same kind of a thing, but only thing what you do is when you choose the starting guess now, so since you have got this d1 already, so you subtract this d1 from your starting guess. So that means you'll have to take out d1 from your whatever guess you choose. So now we, rather than let me say the starting guess here would be I can still say that x1 bar and x1 bar would be like, so I will have say x1 bar, and the x1 bar is the same initial guess maybe which you would have actually used to get this and this. You use say maybe same initial guess or a different one, but from this now you subtract this d1. So minus say some multiplying factor beta times or beta 1 or whatever you want to use into d1. So now your starting guess could be the same what you actually used to get the first mode, the lowest frequency, using inverse iteration approach, but then from that you are subtracting this. But then how do we choose beta? We will have to make sure that this our guess here x1 bar is orthogonal to d1. That means it does not contain d1. So if it is not containing d1, when at the end when we our new x vector would converge, it would obviously converge to the next largest value of lambda or smallest value of omega n, that is omega n2. So now we choose beta such that x1 is orthogonal to essentially d1. That is essentially what I am saying, that this x1 bar transpose, and of course with respect to matrix A into d1, this is equal to 0. So if you do this and then of course A into x1 bar, you are going to get, say you can call that as new vector x2, and again of course this process, again whatever new vector, after once multiplying this x1 bar with A, you are going to get a new vector. That vector again you have to do this process, because when you start initially and do this, it will not guarantee that that vector would remain orthogonal to d1. So every iteration you actually have to subtract beta times d1 and find a new value of beta, and then you again pre-multiply by A, again subtract d1, and again pre-multiply by A, subtract d1, like that you continue. So at the end finally whatever vector you get, let us say you will get x bar m plus 1, this vector would actually then be proportional to, so let me just say proportional, because there would be some constant you can always arbitrarily assign, it would be actually proportional to d2. This is after multiplying this whole vector by m, A matrix A m times. So then resulting vector is going to be d2, and then you use a similar kind of formula, you get second lambda, and that would be corresponding to omega n2. So once you have got let's say omega n1 and omega n2, now you want to get omega n3. So rather than now you start with an initial guess, say x1 bar would be like x1 minus beta 1 times d1 minus beta 2 times d2, and then this x1 bar has to be perpendicular to d1, the orthogonal to d1 with respect to a as well as d2. So like that you find out beta 1, beta 2, then pre-multiply by a, whatever you get again first subtract d1 and d2, and then again pre-multiply by a, and if you repeat that, finally let's say whatever vector you will get, that then will be proportional to d3, the third mode shape, and then you do this multiplication, you get the corresponding eigenvalues. So this is actually known as what is referred to as deflation, matrix deflation. So that means we are subtracting a particular mode out of this. So I think this is what I wanted to essentially briefly discuss about eigenvalues. Now if you want to read more, you can read PCSU also has a chapter on this, so it gives more details about other methods as well. And you can also much more detail means then you refer to actually book by PATEL. So there is a chapter on eigenvalue solution techniques, and you get a number of them. But all of them would be based on one of these concepts basically, extension of these concepts. So I think this is what I also wanted to give you some problems, so maybe I'll give in the next class. So the next class I am going to start error analysis. So convergence and error analysis, that would be the next class topic. And if you have any doubts, questions, you can ask outside the class.
How many lectures after the next class?
Pardon?
How many lectures?
I think now we are left with 2 lectures. So I am thinking of doing 1 lecture, this convergence and error analysis, and maybe 1 lecture nonlinear problems, initial stress, initial strain. So that is what is my plan.